This is lesson 3.3, Properties of Determinants. By now, you should be well versed, well practiced in finding the determinant of a matrix. And now we're just going to go through a kind of a hodgepodge of theorems that just relate to various properties about determinants. So our first one is the determinant of a matrix product, which just simply says that if A and B are square matrices of order n, then the determinant of A times the determinant of B is the same as the determinant of A times B. In other words, if I have two square matrices, I can find their determinants first and multiply them together, or I can multiply the matrices together first and then find the determinant. In either case, I should get the same value. So we're going to just look at an example to see that this works, at least for that example. We've got two matrices, A and B. So again, looking at that theorem, let's do left side first, and then we'll do right side. So let's find the determinant of A, and then the determinant of B, and multiply those together. So A is negative 12 minus 4 is negative 16. The determinant of B is negative 3 minus 20 is negative 23. And so the determinant of A times B is negative 16 times negative 23 is 368. All right, now let's do the right side. We're going to multiply A and B together first and then find the determinant. So first row, first column, negative 6 plus 16 is 10. Negative 10 minus 4 is negative 14. And then second row, we've got 3 plus 24 is 27. And 5 minus 6 is negative 1. So now if I find the determinant of that matrix, so the determinant of A, B, negative 10, and then plus 378. Oops, 378. Wow, that's messy. Let me just rewrite that. 378 is 368. So you can see we get the same value regardless of the order that we do it in. Not a proof to the theorem, but it just shows by example the truth of it. All right, let's look at another one. Determinant of a scalar multiple of a matrix. So this says if A is a square matrix of order n and C is a scalar, then the determinant is either the determinant of C times A or C to the power of n times the determinant of A. Now, typically where we'd use this is if I wanted to take out a scalar. Maybe I see that all the numbers in the matrix have a common factor, and by taking out that scalar, it can make the work of finding the determinant easier. Just remember, though, that when you do that, if you're going to find the determinant and then multiply by the scalar, you're not just multiplying by the scalar, you're multiplying by the scalar to the power of n. So in our matrix, we've got a pretty simple 2 by 2. Now, we could easily just take the diagonals and subtract, right? We do negative 20 times 30 is negative 600, minus another 100 is negative 700. That's the determinant done. But just to show you by example then that we get negative 700 using this theorem, if I took out a 5 and wrote this matrix as negative 4, 4, 1, 6, to find the determinant of A, I'm going to take 5 squared, because my order is 2, times the determinant of negative 4, 4, 1, 6. So now I have 25 times negative 24 minus 4 more is negative 28. And indeed, that is negative 700. Now, just mathematically, hopefully it makes sense as to why it's 5 squared and not just 5, because when I pulled out that 5, I didn't just really pull out a 5 in terms of finding the determinant, because when I multiply the diagonals, I would have a 5 times a 5 in there, right? Negative 20 times 30. Both of those terms are multiplied by 5. And so when I multiply them together, it's actually being multiplied by a 25, not just a 5. That's why we need to take 5 to the power of 2, or in general, the scalar to the power of n. All right, next one. Determinant of an invertible matrix. A matrix A is invertible if and only if the determinant is not 0. In other words, a matrix has an inverse if the determinant of the matrix isn't 0. So in our example, we are told that this does not have, that basically this doesn't have an inverse, right? That the determinant is 0, therefore it won't, by that theorem, have an inverse. We're going to try to find it anyway. So we're going to set up a matrix and just to see that, oh, sure enough, when I try to find the inverse, it doesn't work. So I'm going to take this matrix and I am going to attach to it the identity matrix. And we're just going to do some elementary row operations here to basically try and find the inverse. So kind of think of this as a partition matrix. On the left side, we have our original matrix. On the right side, we've got our identity. We're going to use those row operations to try and make the left side the identity matrix. And so then the right side becomes our inverse. So to do that, I am going to start, let's see, I'm going to focus on that third row, and I'm going to try to make that third row 0, 0, 1. So I'm going to take the opposite of R2. I'm going to take the opposite of R2 and add that to R3. And we'll just store that in R3. So 1 and 2 don't change. 0, 2, negative 1, 1, 0, 0. 3, negative 2, 1, 0, 1, 0. And then taking the opposite of 2 and adding it to 3 is 0, 4, let's see, negative 1 and negative 1 is negative 2, 0, negative 1, 1. All right. So again, continuing to try and get rid of the 4 now to make it 0, 0, 1. I am going to take the opposite, let's see, not quite the opposite, but negative 2 times R1. Add that to R3. And so in this case, again, 1 and 2 don't change. And then multiplying the first row by negative 2 and adding it to row 3, 0, 0. 2 and negative 2 is also 0. And so we'll notice here, as we finish this off, that we now have all zeros in that last row, which means I cannot turn that left side into the identity matrix. Therefore, the original A does not have an inverse. Okay. So again, doesn't prove the theorem, but just gives us an example of yep, sure enough, the determinant was 0, and we couldn't find the inverse because 1 doesn't exist. All right. Next one. Determining if a unique solution exists. So this says if A is the coefficient matrix for a system of linear equations, and the determinant of that coefficient matrix is not 0, then the system has a unique solution. So in other words, thinking about the different outcomes of solving a system of equations, either an infinite number of solutions, no solution, or one unique solution that makes them true. As long as that determinant is not 0, you'll have that last case where you have one single solution. If it is 0, then it's going to be one of the other two cases. It doesn't tell us which one, but we know it's either then infinite or none. So does this system have a unique solution? Well, let's go ahead and let's create the coefficient matrix. And we are going to find the determinant of that coefficient matrix to see whether or not the determinant is 0. All right. Now, we know how to do this. I am going to go through this, but instead of just jumping right in and finding it, let's think back to our last lesson where we can manipulate this matrix a little bit first to maybe make the work for us easier. So for example, if I take the opposite of the first row and I add it to the third row, my matrix 1 and 2 stay the same, but adding the opposite of row 1 to row 3 gives me 3, 0, 0. So again, now I can focus on that third row in finding the determinant, and because 2 of the 3 entries are zeros, I only have to focus on that 3 to get the determinant. So the determinant of A is going to be that entry 3 times negative 1 to the power of 4, row 3, column 1, and then times the determinant of 2, negative 1, negative 2, 1, which is just going to be 3 times 2 minus 2 is 0, is 0. So in this case, because the determinant is 0, there is not a unique solution, okay? Now, I don't know what that actually means. I don't know if there's infinite solutions. Obviously we can look at this and tell, right? Because basically what would happen here is because the one is not exactly a multiple of another, it's a case of no solution then, because we don't have two lines overlapping. But generally speaking, kind of hit a rabbit trail there for a minute. But basically, when you get 0 for a determinant, it just simply tells us that there's not one unique solution. Okay. Again, it doesn't tell us that it's infinite or none. We just know that it's not one. All right. These last two, I'm not going to go through any examples, so I'm just going to kind of finish up by making you aware of these theorems. Because they're pretty straightforward. I don't think an example is really necessary, and you'll practice some of this in your exercises. But the last two, the first one says that the determinant of an inverse matrix. So if A is a square matrix of order n, then the determinant of the inverse matrix is the same as 1 divided by the determinant of A. Okay, so if I find the inverse and take the determinant of the inverse, it's the same as just 1 divided by the determinant of the original A matrix. And then the last one, kind of a similar type idea, determinant of a transpose. So if I have a matrix and its transpose again, switching rows to columns, columns to rows, the determinant of the matrix is the same as the determinant of its transpose. That should seem pretty straightforward because, again, if all I'm doing is switching the rows and columns become columns, columns become rows. And to find a determinant, I can decide which row or which column I'm going to focus on. Well, in A, the row that I pick would be the column in the transpose. So we can expect to get the same determinant there. So again, I'm not going to go through any examples of those. You'll practice that in the exercises, but just want you to be aware that those exist. So that is it for this lesson. Again, this is all about just those properties, things to be aware of, things to recognize when we talk about determinants. And in our last lesson of the chapter, then we'll get into some applications of determinants. I'll see you then.